Hello there, Mr. Sutton here, bringing you this lesson on theoretical probability. In this one, we're going to be studying theoretical probabilities, but we're also actually going to throw in experimental probabilities. And we'll use the theoretical piece of this, at least, to figure out the probability of drawing a certain kind of card, although pretty much every problem here is a real-life application sort of problem. To start this lesson off, we're going to do an interesting warm-up here. What is the probability, by whatever definition you're using of that, of a coin flip coming up heads after 99 out of the first 100 flips come up heads? Pause the video and consider. Now, some of you are probably thinking, well, 99 out of 100 seems like a pretty good number. I mean, they gave it to us. Some of you might also be thinking, well, a coin only has two possibilities, heads and tails, and if it's a fair coin, it's equally likely we'd get either, so maybe 1/2 sounds a little bit better. The answer is you're both right. It depends on what type of probability we're talking about. But more on that later. For now, let's define probability in general. Probability is the likelihood that an event will happen. And there's a whole spectrum, which I'm going to call the probability line here, from 0 to 1. So we've got impossible, that's a 0 probability, and 1 or 100%, that's a complete certainty. Now we can express probability, as you see down here, as a decimal, a fraction, or a percent. So if you get some of these middle values, like 1/2, we could also call that 0.5 or 50%, and there's a whole spectrum of in-between values that we can get. A couple more definitions before we move on here. The sample space, when we talk about it, is talking about all the possible outcomes. For example, in this experiment up here, heads or tails would be our sample space. We have a sample space size of 2 here. There's 2 possible outcomes. And we have a special notation for talking about the probability of something happening. If we say P of A, we're talking about the probability of event A happening. So up here, we would be asking for P of heads, probability of heads. Now that we've explored general probability and how we can express it, let's talk about a specific kind, theoretical probability. And notice I've reframed our warm-up question to be, what is the theoretical probability of that coin flip coming up heads? So theoretical probability is the likelihood of an event happening based on possible outcomes. This is the key word here, possible. So the formula for this, theoretical probability, is just the number of favorable outcomes divided by the total number of possible outcomes. So down here, for example, and by the way, before we go into this example, this is assuming that all of the outcomes are equally likely. So we're assuming down here, for example, that this is not a rigged coin, a weighted coin, it's a fair coin. If we're asking for the theoretical probability of coming up heads, we're saying probability of heads equals, and now we need favorable outcomes over possible outcomes. Well, how many possible outcomes are there for a coin flip? 2, heads and tails. How many of them are favorable? Well, favorable just means it's the ones that we want to happen based on what we said here. If we're looking for heads, there is one way to get heads, and that is by flipping heads. So there's one favorable outcome. So we would say that the theoretical probability of a coin flip coming up heads is 1/2. It doesn't matter what has happened in the past. This is the key. It's all based on what is possible, based on how many outcomes there are and how many we actually want. Now, in general, if the problem doesn't specify the type of probability, then it's assumed that we're talking about theoretical probability. So this is the default probability unless they specify some other kind. We're going to do a little bit more work with theoretical probability. Here's a different situation. A marble is drawn from a bag with 2 red marbles, 2 yellow marbles, 4 blue, and 8 green. And I just drew a little picture of them up here because they're kind of pretty. What is the probability of drawing a red or blue marble? So pause the video and see if you can figure out that probability using whatever expression of it you want based on what we saw before. Okay, so again, we need favorable outcomes over possible outcomes. To find the possible outcomes, we need to add up however many marbles there are, because those are all the possible outcomes is each of these different types of marbles. So we've got 2 plus 2 plus 4 plus 8, and we'll just put that on the bottom of our fraction. And again, we're now trying to find the probability of red or blue. It's amazing what you can fit in this probability parentheses. Now, how many of those outcomes are favorable? These are all the outcomes. How many are red or blue? We have 2 red marbles. We have 4 blue marbles. So there are 6 favorable outcomes if we get any of those 6 marbles. So just adding 2 plus 4 up here, we end up with 6 over, now we should actually add this up. This is going to be, let's see here, 16. And then just make sure you reduce the fraction. So that'll be 3/8. In general, your probability, if it's going to be a fraction, it has to be a reduced fraction. Otherwise, just make it a percent or a decimal. For this next situation, when 2 6-sided dice are rolled, there's 36 possible outcomes, shown below, all the different combinations of 1s and 6s. We want the probability that the sum is more than 3. So if you think about what we're asking for here, there's a whole lot of ways to get a sum of more than 3. I mean, obviously 6 plus 6, but also a lot of these other ones in here. 3 plus 3, 4 plus 3, 2 plus 3, 1 plus 5, right? So do we really want to have to count up all those ways of getting more than 3? It could take a while. So here's a little bit of a hint on this one. Sometimes it's easier to find the probability of something not happening, and then subtracting that from 1. From 100%, in other words. So see if you can use that as a hint. Pause the video and see if you can find a more efficient way to do this problem. All right, let's see if you figured it out. So rather than try to find the probability of getting a sum that's more than 3, I want to find the probability that that doesn't happen and that I get a sum of 3 or less. That's the alternative to getting more than 3. So how many ways to get 3 or less? We've got 1 and 1. That adds up to 2. We've got 1 and 2, we've got 2 and 1, and if you look at all the other diagonals thereafter, they always add up to something bigger than 3. So there's only 3 ways to get 3 or less for a sum, which I could reduce to 1 over 12. Well, I don't really want this probability. I want the probability of this not happening. I want the reverse here, the probability of greater than 3. So since there's no other possibilities, it's either less than or equal to 3, or greater than 3, I can subtract 1/12 from 1, 100%, to get my final answer of 11/12. Now, another way you could have done this is just count up the 33 ways out of 36 that you could have gotten more than 3. I think this is a little faster, though. For this next bit, we're going to give you a little bit of background knowledge. One of the standard problems in probability deals with what is called a standard deck of cards. So if you don't actually know what's in a standard deck of cards, that's okay. We're going to do a tutorial now. If you do, fill in the blanks and move on. But this is really important stuff if you don't know it to be able to do any of these types of problems. So, standard deck of cards. We have 52 cards in that. And out of these 52 cards, there are 2 colors, red and black. Each of these colors has 26 cards each. Each of these colors also has 2 suits per color. So that's a total of 4 suits in the whole deck. Let me give you a visual here. So we've got 4 suits. Here they are. The black suits are spades, or actually this is clubs and spades. And the red suits are hearts and diamonds. Now, each of these suits has 13 cards. You could actually think of these suits as different families or castles or whatever, kind of like a Game of Thrones setup. We have the cards 2 through 10, and I'll just display this for the diamonds here. 2 through 10. We also have a jack, a queen, and a king, and we have this ace here. Now, you might wonder why I put the ace last. In most games, the ace is actually the best card to have, but numerically, it actually only has a value of 1. And these jack, queen, and king cards, because they have faces on them, are called face cards. Now again, I only displayed all of these for the diamonds, but in fact, there is also, for example, a 7 of clubs, and a 4 of hearts, and a queen of spades. So they all have these 13 cards, which means that each of these numbers has 4 different versions of it in a deck. So that's a little bit of a rundown of a deck of cards. Now let's do some problems with these. All right, time to see how much you know about a standard deck of cards. Let's say we pick a card, any card out of that standard 52-card deck. We want the probability that the card is each of these following items. So we'll do the first one together, and then I'll let you try the next 3 on your own. So let's say we want the probability that the card is a king. So again, we're looking for favorable outcomes out of total possible outcomes. Well, the total possible outcomes is the total number of cards in the deck, 52. So our denominator actually on all of these is always going to start off as a 52 before we reduce anything. Now, how many favorable outcomes are there? Well, how many kings are there in a deck? There are 4, 1 for each suit. So then the probability of getting just any old king is 4 out of 52. which we can reduce to 1 out of 13. All right, pause the video and see if you can find these other three. All right, let's see how that went. Not a face card. So we have to figure out how many cards are not face cards. Well, there are 12 cards that are face cards, right? The Jack, Queen, and King of the different suits. So a quick way to do this would be to just subtract the face cards from the whole deck. So we could say 1 minus 12 out of 52 is going to give us not face cards. So 1, we can turn that into really a 52 over 52. So this is 40 over 52, which we can then reduce. If we reduce by 4s, we can reduce that to 10 over 13. So you're going to get really good reducing with 52 here. Now the next one, a black 3. Well, how many of those are there? So there are 2 3s that are black. That would be the 3 of clubs and the 3 of spades. So 2 out of 52 then is that probability, which we can reduce to 1 out of 26. And then finally, a diamond face card. So how many face cards are diamonds? Well, again, we've got queens, kings, and jacks, and diamonds is just one of the suits, so there's going to be 3 diamonds that are face cards. So that's going to be 3 out of 52, which we actually can't reduce at all. At this point, now that we've talked a whole bunch about theoretical probability, we're going to revisit our warm-up problem yet again, and this time I've rephrased the problem is, what is the experimental probability of a coin flip coming up heads after 99 of the first 100 flips come up heads? So this idea of experimental probability, this is the probability that's based on the actual results of repeated trials. So this isn't based on what could happen, this is based on what actually has happened. Experimental probability as a formula is the number of successes divided by the number of trials. So we have to have already tried the experiment a few times in order to calculate an experimental probability. Down here, for example, we've tried this experiment 100 times, so that would be our total number of outcomes, possible outcomes. It's just our number of trials, and we've had 99 successes if we wanted heads. So our experimental probability for that warm-up problem is going to be 99 out of 100. We're going to do another problem with experimental probability, and I've picked one that really highlights the strengths of experimental probability. This probability is great when you're trying to assess a situation where we don't have outcomes that are equally likely. For example, Rondo, when he used to be on the Celtics, what are his chances of making a free throw? That's basically when someone from the other team hits you and you get to take free shots at the basket, for those of you who don't watch a lot of basketball. So it's not equally likely that he's going to make versus miss the free throw. There's a lot of different factors that come into play. So in situations like this, we want to look at data of things that have already happened to try to predict what's going to happen in the future. So pause the video and see if you can use the idea of experimental probability to figure out Rondo's probability of making his next basket. So here are 3 games that he's played, and here are the different outcomes from those games. Okay, so when coming up with our experimental probability, we need to know the number of successes and the number of trials. The number of trials is just all these different free throws that he took in these various games. So add all these together. And if you carefully add these, you will see this comes out to 39. And now the number of successes, that's just the free throws that he actually made, 5 plus 8 plus 9. That comes out to 22. So then his experimental probability of making a free throw is going to be 22 over 39, which if we do on the calculator, we could convert this to a percent like they actually do in basketball. This is going to be about 56.4% if you move the decimal, which is actually not too far from Rondo's actual free throw percentage. All right, Rondo, fire away. So here's his first attempt. Oops. Next attempt. Oh, that one went through. I think it went through the basket unless he missed on the left side there. And then here's his third attempt. Yeah, he actually did do that in a game. All right, moving on. We're going to do one more example here with probability. In the United States, a survey of 2,184 adults found that 1,328 of them have at least one pet, and the types of pets are shown in this figure over here. We want the probability that a pet-owning adult chosen at random has a dog. So first off, what type of probability do you think makes the most sense here? Theoretical or experimental? Well, theoretical means there's an equal chance of owning a dog versus owning a cat, a fish, or a bird. And, that's kind of hard to tell with human beings what they have an equal chance of wanting. So theoretical probably doesn't make as much sense here. Experimental is a good one here because we actually have data collected on what these adults chose. So we're going to do experimental probability that we have a dog. So now we have to ask, what are the number of trials and what are the number of successes? Well, I think we can agree the number of successes, looking at the chart here, there are 916 adults who own a dog. What are the number of trials? So there's two numbers to choose from. We have the 2,184 adults that were actually surveyed, and then we have the 1,328 of them that have at least one pet. Let's reread the problem. What is the probability that a pet-owning adult chosen at random has a dog? So we're already kind of assuming that we're choosing from this pool of pet owners, and we just want to know out of that pool how many have dogs. So our probability then is going to be 916 over 1,328, just the way the problem's worded. And if you run that number on the calculator, it comes out to about 69.0%. Feel free to check my math. That's it for theoretical probability. Until next time, this is Mr. Sutton signing off. There's a high probability we will meet again.